pleasure for me to welcome Paola D'Aquino, and she will speak on real closed fields, Peano arithmetic, and saturation properties. Looking forward.
Thank you very much, and thank you very much to the organizers for inviting me to this meeting. It would have been nice to be in Toronto instead than here with a lot of heat. Here I can talk about these three topics where I've been involved in research, and many of the results I'm going to talk are in collaboration with Salma Kuhlman and other people. Well, the thing is that I don't know how to go from one. Okay. So everybody knows this real closed field is a model of the theory of the order field of the real numbers in the language.
We still see the title page.
I don't know, Zoe, what to do. I mean, so I'm sorry. The real closed field, is a model of the theory of order field with the order field of real numbers in this language. We already everybody knows. Very basic properties. RCF is decidable and is considered tame because there is a good description of the definable sets. On the contrary, I spend a bit more time on the theory of, I'm sorry, but on the theory of Peano arithmetic, because maybe not everybody is familiar with it. The language is the language of order rings, and it's an axiomatization given by basic axioms on the operations of plus and time. And what determines the characteristic of Peano arithmetic is the scheme of induction. So we have induction on every definable sets. And by restricting the complexity of the formula where we apply induction, we have different subsystems of Peano arithmetic. I wrote here just a couple of them, which may be a bit more interesting. Certainly the bottom one of IOpen. And where IOpen has induction only on formulas without quantifiers, while I delta 0 has induction on formulas with bounded quantifications. But this is not so crucial at the moment. So a model of Peano arithmetic, I'm going to describe what it is a discretely ordered ring. So there is, it satisfies this further axiom. There is nothing between 0 and 1. And I will not make any distinction between the positive and the negative part, even if the axioms I showed before are for the positive part, but I will consider a model of PA the ring. And this is contrary to the real closed field, is undecidable and very wild. There is not a good description of the definable sets. And this makes what makes everything difficult. I mean, this was also mentioned by Alessandro Berarducci, no, by Alex maybe in the talk yesterday about the undecidability of Z inside CX. So the overspill is a property of models of Peano arithmetic because it allows us to extend some notions from the standard model, which is N, everybody we know N or Z, to also non-standard models of PA, where for a non-standard model, I mean a model which is not isomorphic to the natural numbers. And so if a formula is satisfied by all the natural numbers, which always lie in as an initial segment of a positive part of any model of Peano arithmetic, then there must be an element which is non-standard, which is above the N, which satisfies it. So if R is a an order field by an integer part, short is IP. For R is a discrete ordered subring I, such that for any R in R, there exists an I in the ring, such that little r is between two consecutive elements in I. And if R is Archimedean, then Z is the unique integer part. So a natural question which has been considered in the past 30, 40 years is, and also solved, what are the real closed fields which have integer parts? Or which properties can or has to satisfy an integer part of a real closed field? So, as I mentioned, I open is the fragment of PA where induction is applied only to quantifier-free formulas, called also open formulas. And there is a characterization due to Shepherdson that the following two are equivalent. That a discretely ordered ring is a model of I open if and only if there is a real closed field for which I is an integer part. This is due to Shepherdson, goes back in the 60s. And the proof uses elimination of quantifiers for real closed fields, and also that we can describe, we can first order define the kth root of polynomials, of a polynomial. The connection with more connection between real closed fields and models of Peano Arithmetic comes from a result by Mourgues and Ressayre, also mentioned yesterday in the talk of Alessandro Berarducci, where they prove that every real closed field has an integer part. And they use a power series construction, which I recall briefly. And if you take a field K and an ordered abelian group, then we consider the field of a power series where the support is the element of G where SG is different from 0, and that this has to be well ordered. So endowed with this can be endowed with a field structure, and if K is ordered, then also we can define an order on the set of this power series, and where S is considered greater than 0 if SG0 is greater than 0 in K, where G0 is the minimum of the support. Let's see, here something is missing, it's the minimum of the support. So if K is real closed, then also, and G is divisible order abelian group, then this is also a real closed field. So the construction, I briefly recall the construction of Mourgues and Ressayre, how they get an integer part. You start with a real closed field, and then you take the residue field with respect to the natural valuation on the ring R, and the value group G with respect to this valuation, and there is an embedding of R into this power series, which is truncation closed. And this means that any initial segment of a series, you can cut a series, which is, if you take any series...
Buon pomeriggio. Oh. Come posso aiutarti?
I'm sorry, but sometimes series comes up and I don't know. I cannot make shut up. So any initial segment of a series in FR is still in FR. So this means the truncation closed. And then if we consider I, this I lives in the power series. So we take the elements of negative valuation which are in the image of F, of R via F, and as complemented with Z, so this is on the level of the additive structure, then this is an integer part of the image of F, of R via F in the power series. And if we take the counter image of curly I, we get the integer part of R. This is a fundamental result that they proved that was necessary also for what was recalled by Berarducci yesterday. There are real closed order fields which don't have any integer part, and these were obtained by Bugatas. And also he proved that for every order field there is an ultra power which admits an integer part. So order field can behave very differently with respect to IPs. And Shepherdson constructed a recursive non-standard model A of open induction. I mean, all non-standard models of Peano arithmetic are not recursive, which means that the operations are not recursive. And this goes down all to the various fragments that I mentioned at the beginning. But Shepherdson constructed a non-standard model of open induction where the operations are recursive. And these are based on a construction with Pussy series. And this is A is an integer part of the real closure of the field Q extended, the field of rational functions of Q, where it's thought x greater than n. And this is a model of, since it's an integer part of this real closed field, is a model of I open for his characterization, and it is recursive. So working with this, starting with this result of Shepherdson, in '96, Berarducci and Otero constructed a real closed field which has a normal integer part. So not only a model of open induction, but it's also normal, which means that it's integrally closed in its fraction field. And I is moreover recursive, so the operation of plus and times are recursive. I mean, this is not an easy construction at all. And normality is an axiomatizable property expressed here in this axiom. And it is like Z is into Q. So normal model of open induction do not solve non-trivially these equations. And the integer part constructed by Mourgues and Ressayre that I mentioned before, this is not normal. And so a real closed field may have two different integer parts, is not unique, as this is the one of Berarducci and Otero. It has an integer part like Shepherdson, like Ressayre, Mourgues and Ressayre, but it has also this another integer part, which is, and the two are not isomorphic, and and they cannot be isomorphic because they are not elementary equivalent. So this is one of the interesting problems that stays. What is? R is no standard. Yes, R is no standard. Alex, yeah. Okay, so it may have two different integer parts. So natural questions that arise are the following. Does a real closed field always have a normal integer part? And this question is, and related to this is question 2, is there any relation among different integer parts of a real closed field? These problems are open now have been open for quite a long time. Various people have made attempt to find an answer. Included, we tried to work on it with Salma. There was somebody called Azatrian who claimed that he had some results, but never came out the results, and is out of research as far as I know. So these are still open and interesting problems as far as I know. I don't think that they are easy, but they are very interesting. But then there is another question, number 3, which asks which are the real closed fields which have integer part which models the full Peano arithmetic. And this question has an answer, and this is joint work with Julia Knight and Starchenko, Sergei. And the property which characterizes the real closed fields which have an IP, which is a model of PA, is recursive saturation. This is a property which is very connected to models, natural for models of Peano arithmetic. And I review a few things. Oh God. Okay. So if we start with a computable language, because computable language, and we take a structure, an L structure, then A is recursively saturated if for any computable set of L formulas, and for any tuple of parameters from the finite tuple of parameters from the structure, if it's consistent with the theory of A, then the type is realized in A. So any finitely satisfiable subset of gamma AX, then if it is finitely satisfiable, then is realized in A. And a structure which is another way of saying defining recursive saturation is that there is in M there is no recursive counterexample to omega saturation. And the standard model of Peano arithmetic and also R, the reals, these are not recursively saturated because of the type, this one. So, but there is a kind of saturation in models of Peano arithmetic. Here I reviewed basic things about PA, models of PA. So there is no definition of satisfaction for any model of Peano arithmetic. So there is no formula. Here there is T has 2 variables, not 1, such that witnesses that a formula is satisfied by a tuple A. And also there is what I was saying, a certain amount of recursive saturation in each non-standard model of Peano arithmetic if we bound the complexity of the formulas. Bounding the complexity of the formulas is to restrict the formulas to the classes that I mentioned at the beginning, where we apply induction to certain classes of formulas, and the complexity of the formulas are determined according to alternation of quantifiers. So for each n, we have a certain amount of saturation, and this is used to is a powerful tool in studying non-standard models of Peano arithmetic. So the result that we got with Julia Knight and Sergei Starchenko, I can summarize them in the following results. That if R is a countable real closed order field, then if R is recursively saturated, then there is an integer part which is a model of PA. And in fact, the the real closure of this integer part coincide with R, with the starting real closed field. And moreover, what we can, it's not difficult to using recursive saturation to obtain integer parts which satisfy any property which is consistent with I open. So the basic is I open, but then we know that I open is very pathological, so many properties are consistent. So we can have, for example, an integer part which is where exponentiation is total, and also an integer part where exponentiation is not total. Oh, that's it. So, and on the contrary, if we take a real closed field which has an integer part which is a non-standard model of Peano arithmetic, then R is recursively saturated. And if R is countable, we have an isomorphism between the starting real closed field and the real closure of I. So for countable recursively saturated, for countable real closed fields, having an integer part which is a model of Peano arithmetic is equivalent to be recursively saturated. It turns out that two countable non-standard models of Peano arithmetic have isomorphic real closures if and only if they have the same standard system. And this is a notion that I'm going to introduce. So I need to, because this will be useful, will be needed also later. What is a Scott set? So it's a collection of subsets of the natural numbers which are closed for Turing reducibility and for disjoint union. This means for disjoint union. And also if there is an infinite tree which is in S, then there is a path of the tree which is also in S. So this is up to coding, of course. Any Scott set is a real closed field. We can induce an Archimedean field structure on it. So it's a subfield of the reals. And there is a characterization due to Scott that which puts a relation with the models, non-standard models of Peano arithmetic. So if A is a non-standard model of Peano arithmetic, we take any element in A, we consider the set of n such that the nth prime divides A. So these are called the coded sets in A. So there is a subset which is coded in A. Of course, there are, for that property that I mentioned at the beginning, for those who have never worked in Peano arithmetic, there are no standard primes also because of the overspill. So the collection of these subsets of the coded set form a Scott set. And it corresponds also to the definable sets with parameters in the model M. And M, of course, is a non-standard model of PA. Here there is a bit of a mess up with the curly A and M. These are all models of Peano arithmetic. So what is true is the following, that this holds for any structure in a computable language, that M is recursively saturated if and only if M is S saturated for some Scott set, which means that M realizes types which are coded in S, and any type realized is coded. So this is a technical thing on which I will not spend any time, because it's the two properties, and this is what I said in a few words, that any type which is coded, which is the type of an element, belongs to the Scott set associated to a model of Peano arithmetic. And if an element, a type is consistent, then type satisfies are then coded. And this is used in the proof that of the characterization of those real close fields which have integer parts models of Peano arithmetic. So if we take, I want to this. If I start with the model of Peano arithmetic, I can consider take an element, a non-standard element. So all the elements which are bounded by standard powers of A. This turns out that is a model of I delta 0. And this clearly you can construct a type which is not realized, a recursive type which is not realized in I. So not every, so this is an example of a model of I delta 0 which is not, whose real closure is not recursively saturated. And the countability of the real closed field is necessary. In the equivalence that I mentioned before, and because there are uncountable recursively saturated real closed fields with no integer parts, which are models of Peano arithmetic. And these are constructed as power series fields. And actually these constructions as power series fields and using valuation theory gives a lot of methods to construct models or real closed fields which be with properties which violate some properties, for example. So, okay, this is just I skip because it's all. And I want to go back to show a real closed field. I want to construct a counterexample to this, that there are recursively saturated, an uncountable recursively saturated real closed field which has no integer part with a model of PA. This can be done in various ways, and I present some. So we take the additive structure and the group of positive elements, the multiplicative group. These are divisible ordered abelian groups, and we can decompose them as follows. So where this is the valuation ring, and this is the units in the valuation, the positive units in the valuation ring. And A and B are respectively a complement of RV and a complement of the UV. So we say that an ordered field has a left exponentiation if there is an isomorphism from the group complement A into the group complement B. It is just an ordered field. If K is a real closed field with an integer part which is a model of Peano arithmetic, I is a non-standard model of Peano arithmetic, then we can show that K has a left exponentiation. I mean, this is done, and this follows also, explains the remark, that if we start with a model of Peano arithmetic, this has an exponentiation in it, defined with, there is a formula defining it, and is provably total. So every model of Peano arithmetic carries an exponentiation. And while for those working in the field know that I delta 0 does not have this. Exponentiation is not provably total. So if we add an axiom which guarantees the totality of exponentiation, then we can reproduce the same proof as in the theorem. So we can define over K an exponentiation starting from the exponentiation over the integer part. It's a bit technical. You first define extend to the negative part and then to the quotient. And there is a result going back to 97 by Franz Victor Kuhlmann, Salma Kuhlmann, Shelah, that says that for non-trivial ordered abelian group, the field, the power series field over R and G admits a left exponentiation. So if we take this, any of these fields cannot have an integer part, which is a model of PA, because having an integer part model of PA, we saw that gives a left exponentiation. We can define an exponentiation on it. So this is a first example where there is not an uncountable real closed field which doesn't have any integer part. We still want to involve the recursive saturation property. So, well, I mean, this is well known to everybody, I guess, the notion of alpha saturation for a structure. If we take any subset, these are the parameters of cardinalities less than alpha, then every set of formulas with parameters in A, which is consistent with M, then it's realized in M. This is saturation. And this is also in valuation theory. Everybody knows the notion of pseudo-Cauchy sequence. Which I will use now to recall there is a characterization in terms of valuation. As I said before, expressing properties in terms of valuation theory helps to construct many models which characterize in a different way properties and give a way of constructing models. So if we take G, a divisible order abelian group, and alpha is, okay, at least countable, then G, there is the following characterization, that is alpha saturated if and only if the value set with respect to the natural valuation is an eta alpha set. All Archimedean components of G are isomorphic to R. And every pseudo-Cauchy sequence in a divisible subgroup of G with value set of cardinality alpha has pseudo limit in G. Now these properties, okay, if the structure is alpha saturated, they follow quite easily. The opposite, the three properties, this trichotomy that we will find also in the case of real closed fields, are necessary to consider the various cases which can be presented, because if we take a type which is consistent with G, and this will be the same argument also in the following, the other cases I'm going to talk, this will be realized, we will find always an elementary extension where it is realized. And then for the position of the realization in the extension, we have to use, according to how this the realization in the extension is related to the starting order abelian group, then we use the three properties. This is roughly the idea. From the previous characterization, this holds that if this is a result already in some notes by Harnik and Ressayre, and then we developed with Salma and Karen Lange, that if G is divisible ordered abelian group, then G is recursively saturated if and only if the value set is nothing else than a dense linear order without points, and this is the case also for Aleph-0 saturation. And all Archimedean components of G are isomorphic to a Scott set, a single Scott set. So there is a Scott set to which all the Archimedean components of G are isomorphic, always here related to the natural valuation on G. So we can we have the following corollary, that the countable ordered abelian group G is recursively saturated if and only if G is isomorphic to the AND product of a Q of some countable Scott set. Okay, this is more in general what we get from if we avoid the countability hypothesis of the model. And for real closed fields, the characterization is the following: that a real closed field is Aleph alpha saturated if and only if the value group is Aleph alpha saturated, and the residual field is isomorphic to R, to the reals, and every pseudo-Cauchy sequence in a subfield of absolute transcendence degree less than Aleph alpha as a pseudo limit in R. Now, in both cases, this third condition, we need in the three cases, in both the cases of divisible order abelian group and real closed fields, we use a valuation inequality, which we know is true both in the case of the group, divisible order abelian group, and also in the real closed field, using O minimality. Because we have this is mainly the problem arises when we want to show Aleph-0 saturation, because of cardinality reasons. Because when we go and consider the substructure, which in the case of the group is a subgroup, where is it? Okay, in the subgroup. Or in the case of the field is a subfield. So this hypothesis put a bound on the cardinality of the definable closure of the parameters. And so this is needed only in Aleph-0 category, in Aleph-0 saturation. Okay, this property in for recursive saturation comes to this 4 equivalence for recursive saturation. And this is obtained together with Salma and Lange. That real closed field is recursively saturated if and only if there is a Scott set. So the residual field is isomorphic to this Scott set. In the case before was the reals. And the two conditions here, that every pseudo Cauchy sequence of length omega in a subfield, in any subfield of a finite transcendence degree of a Q, that is computable in an element of sigma of S has a pseudo limit in S. Computable is in the recursion theoretical terms. And there is also a fourth property here, that every type realized is in R is computable in an element of S. And we couldn't avoid this fourth property. So if we take, you remember we got an uncountable recursively saturated model uncountable, sorry, an uncountable, we got an uncountable real closed field which does not have an integer part which is a model of PA. And now we can get a recursively saturated one by applying this characterization. So this I skip. Yes, I mean the condition for we cannot avoid that. This was, but well, there is a counterexample which shows that this fourth condition we cannot avoid. But I won't stay because time is passing. So we have also restrictions on the value group of a real closed field which has an integer part, a model of PA. So this is what the analysis via valuation theory can give us more information. We got that there are restrictions on the value group of a real closed field which has integer part model of PA. And this is, I recall that for a countable divisible ordered abelian group, we say that is an exponential group if and only if G is isomorphic to the Han sum over a countable Archimedean group. And if okay, sorry. Okay, so we have that in the case of countability, divisible count so we have an example here. The G is an exponential group if and only if it's of this form. So if K is a non-Archimedean real closed field which admits left exponentiation, then the value group is an exponential group in the residue field. So you remember that if a real closed field has an integer part, which is a model of PA, it has left exponentiation. So the value group is an exponential value group in the residue field. So if this is what I said, and in particular we have, this is what I already mentioned, this is a joint work with Merlin, Carl, Salma, and myself, and in particular we get that the rank of the value group is dense linear order without endpoints. And by constructing, so we get that any field, so we start with a real closed subfield of the reals, G in a divisible ordered abelian group, which is not an exponential group. And so any field we take here between the real closure of the field generated by K, little k, and G, and the power series, cannot have an integer part which is a model of PA. So there is also this question of a natural, is there a natural characterization of uncountable real closed fields with no standard models of Peano arithmetic? This question was also addressed by David Marques, Merle, and Steinhorn in a paper. So the notion they considered was this resplendency, which is strictly related to recursive saturation. Actually, for countable structures, recursive saturation and resplendency is the same, coincide, the two notions, and says that everything, we can expand the language, we can expand the structure. If it's resplendent, we can expand a structure with relations if there is compatibility. And so Mourgues, Merle, and Steinhorn showed that the real closure of an omega-1-like model of Peano arithmetic, this is an uncountable model of Peano arithmetic whose initial segments are all countable. This is not resplendent. They showed also that if M and N are one of the two models of Peano arithmetic omega-1-like with the same standard system, then the value groups of their closures are isomorphic, but at the same time, there are a lot, 2 to the F1 elementary equivalent recursively saturating models of Peano arithmetic, which with the same standard system, such that the real closures are pairwise non-isomorphic. So for the uncountable case, there is not yet any characterization. And I conclude with the following. This is the last one. We saw the characterization of Aleph alpha saturation in terms of valuation theory, and also what we got then for recursive saturation. And with Salma, we managed to get an analogous result for any polynomially bounded or minimal expansion of a real closed field under these conditions. So we take, assuming that the prime model is Archimedean, then the following characterization of Aleph alpha saturation holds. Then, as before, the value group has to be Aleph alpha saturated. The residue field is isomorphic to R, and every pseudo-Cauchy sequence in a substructure with the dimension over the prime model of the right cardinality of absolute transcendence degree has a pseudo limit in M. So this we could prove it using the same procedure, the same proof works, and we made use of the valuation inequality because this holds in polynomially bounded or minimal expansion of real closed fields. This notion was mentioned in the talk of Alessandro yesterday. For the other case, we don't know, and we may continue to work on this, maybe, if in the case of non-polynomially bounded. I mean, the thing is that there is not, in this case, evaluation inequality. So I don't know if maybe a different proof, or we could adapt something else. Again, always for Aleph zero saturation. For the rest, is not a problem. It can be. The proof goes through. It's just a question of Aleph zero saturation, where there can be the parameters the structure generated by finitely many parameters may have two big sides, and we cannot deal with it. So this is what I wanted to say, putting together real closed fields and Peano arithmetic and the tools from valuation theory, which have helped us to understand and characterize more all the results, and also give us some examples of in our settings. Thank you.